Hello, everyone. Thank you for joining us. Today is December 13th, 2025, 10 a.m. And we welcome you to a special presentation on our AWG, Association of Women Geosciences, Pacific Northwest series. And we're honored to have Jean Humphreys, Professor Jean Humphreys from Oregon, give us a talk. And I'll introduce the talk in a second, but first I wish to introduce him. I've known Jean for a long time. We're fellow graduate students, and I didn't really understand what he was doing, but he was amazing, and his background in California in education is terrific. He's been studying tomography and geophysics in the mantle since his first publication, 1975. So he really knows his stuff. He's going to give us a good talk on that, and he's asked me not to go in detail of his background, but he's had many awards, including a fellow from the Geological Society of America and further. But for me personally, he's been a friend through many decades, and I really recognize his mentorship and his encouragement. And so we asked him to give a talk. And his talk title is a little difficult for me, but it was awesome. Yellowstone's plume-triggered gravitational instabilities within North American lithosphere and the making of the Columbia River flood basalt eruptions, insights into major Earth processes. So hand it off to Jean. Thank you.
Okay, well, thanks, Mindy. Let me get my screen up. Let me see. And there we go, I think. Yeah. Okay, I shortened the title. The title I gave Mindy was, I think, too much. Let me clear my screen a little bit here. Okay. Let me go back one. Well, this is an introductory slide, but my interest really is in the Columbia River flood basalts, something I've been thinking about for quite a while. And I have to admit, it's been a confusing journey. There were times when I was really entertaining alternative possibilities. I guess you'll see that as it goes. And as the parenthetic comment states in the title, to understand the CRBs, the Columbia River basalts, you really have to understand, I think, some of the history of the Pacific Northwest as well. So let me get on with it. I think to start, there is, based on observations, you see that there are a series of flood basalts around the world at different times. And for each flood basalt, basically, there's a hotspot track that leads away from it. And for each hotspot track, if you can track it back to the beginning, you find a flood basalt. And that's pretty compelling. So I think Mark Richards in particular put together the story. See, there we go. Where the idea is you get kind of a plume starting from the thermal boundary layer above the core. And it's buoyant, kind of like a lava lamp, and relatively low in viscosity compared to the rest of the mantle. So it rises. But as it rises, the source is feeding plume mantle into the plume head faster than the plume head can rise, and so it inflates. And when this plume head hits the base of the lithosphere, that's when you get a flood basalt. I should mention that before the plume head hits the lithosphere, the buoyancy should lift up the lithosphere and give you uplift before any eruption. Okay, well, after the flood basalt, plate tectonics or whatever, it takes the plume head away, and you're left with a track, a hotspot track above the plume itself. And so this has sort of been dubbed the plume heads and tails hypothesis or model. So I give a quote here. I think all theoretical plumes are happy, but every real plume is unhappy in its own way, after Leo Tolstoy. And I'll say the Columbia River basalt is unhappy in its own way. And we'll get into that. Okay, but to start, I think there are some images of Yellowstone, something with Brandon Schmidt. Here's the Yellowstone track. Here's where Yellowstone is, and you see the plume presumably heading down into the deeper mantle, and also influencing the transition zones as temperature should do. I think Steve Grand and student Nelson have another cross-section, this purple, where they see things in a more global sense, and they too argue that they see a plume going all the way down. Okay, so it looks like Yellowstone is a deep-seated mantle plume. And furthermore, it has all the attributes you would like. The flood basalt is large. You see many, many stacks of flows for the Columbia flood basalts, which actually cover a large area. You see a hotspot track, as you should, and then at the other end, you see an active hotspot, Yellowstone National Park. So it sure looks like a plume's head and tail story. Okay, so I mentioned here that we have this model, the plume model, and it's based on observations. And from those observations, you can make predictions, and there are predictions you can test. I have to add that this model, any model that we have, defines on how we think about plumes. And having that model in mind really has a tendency to trap your thoughts and make testing more difficult than if you had a more open mind to it. But we all think in terms of models. Okay, the CRB itself. Here's just a picture again of many, many layers of the Columbia flood basalts, up to a mile thick in this area. And this is the area covered by the flood basalts. And if you took all that and piled it a kilometer thick, it would cover the state of Oregon. So it's a pretty big event. In the scheme of flood basalts, it's relatively small, but nonetheless, it is a large event. And it is our most recent flood basalt event. And much of the vestiges of this event are still around, haven't faded away. So they give us something more to look at than many other flood basalts. Okay, and this is just to sort of emphasize this whole thing. The flood basalt, you see the area covered, and the whole event started down here. And you see a nice time progression to Yellowstone. And again, this looks like a plume heads and tails model. But I say all is not happy here. One thing is, starting from where Yellowstone began, there are two hotspot tracks. One heading to Yellowstone, of course, another one going across Oregon, ending up at Newberry Volcano, a very large shield volcano. And I just have a couple pictures here. You see a caldera wall and interior, and you see the subsidian flow in particular, from the edge, from the caldera wall. And if you haven't been to Newberry, it really is quite spectacular. The subsidian flow in particular is just incredibly interesting. But anyway, here you have two hotspots leading away from the initial volcanism. And I ask, is this a problem? And in this case, I say there is an explanation that has been proposed. I'm not thrilled about this figure, but it'll serve the purpose. If the plume comes up and the plume head lands in this general area, it's near a subduction zone, and corner flow will draw a sinosphere and some of the plume head, presumably towards the subduction zone before things get dragged down. So this hot plume head being dragged towards the subduction zone in corner flow can explain the propagation across Oregon. And it seems to work pretty well timing-wise and location. So I think I mentioned here, when you have an observation that's inconsistent with your model, what do you do? I think people like Karl Popper would say you throw the model away. It's been falsified by this observation. I think in earth science, which is more complicated than, let's say, physics, that Popper was mostly thinking about, we try to patch up the model. We say maybe things are more complicated than this Earth. There's if these things happening are natural experiments in the Earth, we have many natural experiments going on all at once. So in this case, this patch for why there's a reverse or backwards hotspot track, I think most people are okay with this explanation. So we say maybe we can ignore that problem. So there are other problems. So I just kind of mentioned a list of them here. I take the backwards propagating hotspot and I say, okay, let's scratch that off the list. And Yellowstone is happy in that it looks like a plume heads and tails. Things start where they should by back projecting Yellowstone, and they start pretty much where they should. On the other hand, and I'll go through these, but there's no pre-eruptive uplift. The CRB eruptions get very far off track. They start down here, and very quickly, actually, they get way up to the north. They do that very fast. And as they went north, they got larger and larger in volume. So how do you deal with all this? And I just kind of show a timeline here, which is getting better and better from the various people doing geochronology. You see from the initial eruptions to the large Grand Ronde eruptions took only 150,000 years. In fact, the Imnaha, which started way up here, happened very quickly. I think something like 80, no, you'll see, but maybe 85,000 years. So in the end, with all the problems we're going to encounter, you may wonder, am I going to throw this model away or am I going to continue to patch it up? Okay, and there's more unhappiness than that. Turns out that Silesia accreted 55 or 50 million years ago, and it is generally thought to be created by Yellowstone, the Yellowstone plume. So it is a flood basalt, a large igneous province. And if this is a flood basalt created by Yellowstone, what are the CRBs? Okay. And to say a little more, and I give credit to Ray Wells here, who has worked most on this, I think. The idea is that Yellowstone was off the coast of North America before North America rode over the top of it. And while there, it created two large igneous provinces. One of them we call Silesia, coast ranges in most of Oregon and Washington. And also on the spreading center, the other side, Silesia, or not Silesia, Yakutat, which is now subducting under Alaska and, driving a lot of pretty spectacular tectonics there. So the Yellowstone hotspot seems to have this early beginning. It made this large igneous province, and then it was overridden by North America around 45 million years ago, and all turned quiet. And then things started up again 17 million years ago with the Columbia River basalts. So in terms of the heads and tails model, the CRB is clearly not what initiated Yellowstone, and it's not a deep-seated mantle plume. So what is it then? Okay, and Vic Camp has been thinking about the CRBs for a long time. He proposes that the Yellowstone got beneath the Farallon slab or the Wallowa Mts slab and lifted it up. But the reason you don't see anything at the surface is it's under the slab until it finally breaks through with the Steens basalts and then propagates on towards Yellowstone. And I sort of asked rhetorically, this little plume, and Bill Lehman would say it's about 100 degrees of excess temperature. Can this little plume really lift a wide, cool slab? I give an average temperature of 500 degrees. And it's a strong viscous slab, presumably. So that seems kind of remarkable. However, I got to say that if you look at the volcanism, that Vic talks about, there are adacites across Oregon, which he attributes basically to the melting of the basaltic slab, basaltic crust of the slab, and these high potassium magnesium rich or high potassium magmas coming across Oregon, which he takes to be the hydrated mantle, heated up above the slab. So from a geochemical point of view, this seems to make some sense to Vic. Like I say, from the tomography, we have this curious hole in the subducting Wallowa Mts slab. If you take this back 16 million years ago, This at now 125 kilometers would be more near surface, and with oblique subduction, it would be farther south. It seems like it's in the right place and represents the right time to maybe have been disrupted by Yellowstone. If it lifted the slab up and then broke and reestablished a steeper dip, then we do see a trend, a high velocity mantle, cool mantle trending across southern Oregon that could represent the remnants of the slab that got torn before it settled back to its normal steep subduction. So I say here, you could make the case that the Yellowstone plume did lift the slab and finally broke through. So perhaps we're patching up this model once again, but maybe this explains the observations. So I just mentioned here, I guess, what I said, but while the CRB is not derived from a lower mantle plume head in the standard heads and tails manner, plausibly it is the accumulation of plume that ended up under the Farallon slab. And then when it finally got out, we have our own locally created upper mantle plume head. So we saved the plume model perhaps from being discarded. Okay, some other observations. I think this is from Burov in particular, but ascending plume head before it hits the surface gives us what's labeled transient uplift of, several hundred meters. And the idea is the buoyancy of the plume head is lifting up the surface of the earth before any magma is getting out. So this is one of the things people look for. And I go to the CRBs, and the Steens are the first erupted magmas down south, and they seem to fill a broad, low basin. Certainly, they don't represent any regional uplift at this time. So there is no apparent pre-eruptive uplift with the CRBs. Okay. Furthermore, and again, going back to Burov, a plume head, when it hits the lithosphere, should flatten, and at least in their models and other models, you get typical rates shown here, in this case, 300 kilometers in 4.5 million years. For the CRBs, we get eruptions propagating north to where the large eruptions actually came out in northeastern Oregon, and that's 300 kilometers in 150,000 years. That's 30 times faster, roughly, than the models give. And this propagation of volcanism was northward. So it seems very asymmetric. So this seems like odd behavior. And so, with no apparent pre-eruptive uplift, and with this one-sided and rapid propagation, I ask, are these fatal problems? Or can we continue patching this up and save the plume heads and tails model for Yellowstone? Okay, so let me quickly go through some of these eruptions just so you see the spatial distribution and a few basic conclusions. Here are the Steens, and you see the dikes schematically represented on where these eruptions occurred. The next eruptions, 80,000 years later, the Imnaha eruptions, and they came out up here. So you see 120 kilometers of propagation, if you will, in this 80,000 years. And the Imnaha erupted and flowed all the way across Oregon and down into the Columbia embayment, this low-lying area in Washington. They did not flow south. So this big, broad area that accumulated the Steens now is not allowing the Imnaha south. And the typical explanation by people like Vic Camp is that we're lifting this area up and we're damming the Imnaha and it can't flow south. And so in a sense, we're seeing evidence for propagating uplift. Uplift of the Steens area now, keeping the Imnaha going north. Okay, and then on with other flows, no need listing them all, but you see the next one, you see the eruptive centers are a little farther north. The dam is propagated north again, and again, and again, and again, and so on. And here are the final eruptions, the Saddle Mountains eruptions, coming out in Idaho, in Washington, and little bits of Oregon, way far north from where things started. That took about 750,000 years to get there. Basically, these basalts lay down over a kilometer of thickness that are progressively dammed. So it suggests over a kilometer of uplift associated with something propagating north, and in this one-sided way. Well, a side comment here, but I won't stop for that. You can read it later, I suppose. But another curious problem. But I want to mention, maybe by way of side comment, this propagating uplift. The eruptions propagating north seem actually, for all except for the very last eruptions, to be coming from one magma chamber located here. So why are the eruptions propagating north when the chemistry is saying that the origin is staying pretty stationary? And I think a simple answer, maybe not totally original in what I'm saying, other people suggested this, but with uplift, the magma only ascend, hydraulically to a certain level, and it can propagate laterally, much like it does in Hawaii, until it finds an area of lower elevation it can erupt from. And that area keeps propagating north as the uplift propagates north. So perhaps the propagating eruptive centers is not too significant in trying to understand the dynamics of what's going on. The propagating uplift, I think, is more important. Okay, so by the time you get through the CRB eruptions, what you've ended up with is Eastern Oregon high plateau of maybe, I don't know, 1.5 kilometers is a good guess. And so here we are at 15 million years after the whole event is over, except for maybe a few little dribs and drabs from the last eruptions here. Very small percentage. I mentioned this uplift now has been, the topography has been modified. The Snake River Plain obviously has been modified by Yellowstone. What it's doing up here, I won't get to. I'm not sure I know. But we also have this bullseye up here I will get to. But these are both created after this Eastern Oregon uplift, representing subsequent dynamics. So I want to give a brief history of this hotspot. And the reason for doing this is I want to address why the one-sided and rapid uplift. I can't help but also address how I think the Pacific Northwest was largely made. Okay, so here's my view. And I think if you go back to, let's say, 55 million years ago, say before Silesia actually accretes, I believe that we had flat slab subduction underneath the Pacific Northwest. In fact, I'd say I think we have it under most of the Western US. And the hallmark for this, following Dickinson and Snyder actually, is the flat slab is separating North America from the asthenosphere, keeping the volcanism from happening. And yet these basal tractions are driving contraction far inland, not where subduction goes down, but way far east. Okay. It is also hydrating the base of the lithosphere, so that when the slab finally comes off, in one fashion or another, the asthenosphere ascends, decompresses, releases melt, and it's also hitting the base of a hydrated lithosphere. So you get vigorous magmatism, and you just see, remember, Silesia accretes around 55 million years ago. You see all this magmatic activity starting at about that time. So this is the start of the big Western US ignimbrite flare-up, and then it's going to propagate south from here. I don't think I'll say why today, but let's say also associated with this volcanism are core complex extension. So it's night and day. No magmatism, contraction, suddenly lots of magmatism and extension. And I think there's more to be said about that, but I'm going to move on to the CRBs more. So if I take volcanism to represent the foundering of flat slab, here is where I believe Silesia to be. This is the part that's well justified along the western side of the Cascades, actually observed in many places. And you see all the volcanism around. And I say, well, if there's flat slab remaining anywhere, where did the slab not founder? And of course, right there. And this is the area where the Columbia River basalts are going to erupt from. So I envision flat slab under that area until 17 million years ago. Well, it's time to get below the surface a little bit. So some seismic imaging now. Quickly, the tomography. Here's the Wallowa slab for reference. And then we see this high velocity thing, the Eastern Washington and Idaho curtains, we call them. We're at 200 kilometers depth now. So this is deep into the upper mantle. And we see this anomaly, which is going to be the main part of this story. So in north-south cross section, we see the slab from Washington and then turning around and going deep into the upper mantle. That has to be Farallon slab. I'll say a few more words later about that, but I think that's the only reasonable explanation for what that can be. So the slab I envision being here, keeping magmatism from happening, and then these slabs are delaminating, giving rise, the Okanagan and the Idaho, all the Challis and Kamloops related volcanism as they delaminate, but slab remains here until 16 million years ago. That's the way I see it. Okay, and then at 16 million years ago, this slab delaminates south to north, gives rise to this anomaly that I just showed you a picture of. I think later I forget what I put in. I may show you evidence for flat slab still remaining here between all these pieces that have delaminated. Okay, if I don't get to it, ask me, and I think I have it close at hand. Okay, well, I wanted to say a quick word about interpreting mantle tomography. Maybe Karin said that to you earlier, but I'd say if it's faster than 1% fast, and you see the scale down here, the blue stuff is cool. We understand well enough what makes seismic velocity variations in the mantle, and composition really has very little effect. I should say the depletion and extraction of basalt, major things you can do to the mantle don't affect its velocity compositionally wise. But coolness does, and coolness is only made near the surface of the earth. So we are talking about lithosphere here, one form or another. And you see the Wallowa slab as an example. If you go east of the Cascades, but west of the old Cretaceous arc, where it was hot at depth, how do you get high velocity mantle where you had magmatism and thin lithosphere before? There isn't enough North America lithosphere there to account for it. And I think the only thing you can do is attribute that to subducted slab. I think it has to be after the Idaho batholith, after 100 million years. The only slab you could point to for this, I think, is a Farallon slab. So we're seeing a record of the history for the subduction of the Farallon slab. And here it is coming up to the surface now over here and over here. Okay, so a few more words about this delamination. And I say this is the first of 3 lithospheric instabilities that I want to make some comment about. So I envision this slab, again, Washington to the north, and then dangling deep beneath, very northeast corner of Oregon. I envision that as Farallon slab that has now come off. It was flat until Yellowstone came along, and I'd say triggered its delamination to roll back to the north. This could account for then both the propagating volcanism and uplift, and also the anomaly that we image here in the mantle. Okay, and the Yellowstone plume also provides the mechanism for triggering the delamination of this, negatively buoyant anomaly. Okay, so here's just a little picture of what I envision. You see the slab coming off. You see the plume working its way north. It's buoyantly pushing north, but maybe more important, it's being sucked north by the delaminating slab, and the triggering or the actual decoupling here, I'd attribute to the melt itself ponding in this area of low pressure as the slab is coming off. So to get delamination, you need some mechanism to decouple the slab from what's above it, and the melt does that. And you need enough load to pull the delaminating materials down, and the weight of the slab is doing that. So I see this as, I label here, melt-enabled lithospheric delamination of ocean lithosphere. I'll come back to that, but that's unusual for delamination in most people's models. But this can drive the rapid northward propagation. So here I put, where I think the slab was before it came off. And I sort of embellish it a bit here, showing the plume location yellower than the tomography, because this is now 16 million years ago or 17 million years ago, but it's showing where the plume should be. Okay, I want to say a few words about this area to give it more credence. And I'm looking at the time real quick to see if I have the time. Sure, I'll go for this. If we look at this area right here at the Washington-Oregon border, essentially, the crust is quite thick. This is from receiver function imaging, which is a seismic phrase for meaning when a teleseismic or arrival of the waves from a very distant earthquake arrive, when they hit an interface, like the MOHO, a P wave will partly convert to an S wave, and the time difference between the P wave and the S wave can be used to tell us how deep the MOHO is. And you see from this work from Hai and Gao that most of this crust is fairly thin, maybe 30-ish kilometers. Right here, it goes down. And with this migrated image from Young-Hee Kim, you see down to 50 kilometers. So really quite a local thick crust. Okay, in this cross section, you've seen this before, but right here is where it gets very thick. Oh, I do show this. This is another receiver function imaging from Alan Levander, Megan Miller, where they're looking at the base of the lithosphere, the conversion at greater depth. And you see most of this is occurring around 60 or 50 kilometers, something like that. But right here where I made the comment that I think we still have flat slab, you see it comes up to about 75 kilometers. I should say the interface goes down to 75 kilometers. So this very local perturbation here between the delaminated CRB slab, the delaminated Eastern Washington slab, and the delaminated Idaho slab, to me, this is a flat slab turning over and becoming the Idaho curtain. Okay, more seismology, maybe getting too esoteric for some people, but anyway, here is the crustal anisotropy. And the source of the anisotropy is thought to be the deformation of the crust as it flows. And we're looking down here at 5 to 25 kilometers, and you see the fast direction of propagating waves shown with these bars, and they tend to point to Northeast Oregon. And if you really pull the crust down as much as 20 or 30 kilometers, you should get a lot of crustal, well, you need to have a lot of crustal flow in to fill this depression. And the anisotropy seems to suggest even to great distances, to my surprise, you're seeing crustal flow into this area. Okay, stop for a second and take a little global view. People around the world are appealing commonly to delamination for all sorts of tectonics, probably correctly so. And you see a lot of these areas mentioned here. The usual model is shown here. Here's the mantle, there's the lower crust. And the idea is the viscous lower crust, especially the very hot parts of it, are very low in viscosity. And these are the decoupling zones that allow the lithosphere, the heavier lithosphere, to come off and decouple in the crust. And you see various models for that. Always using the crust. For the CRBs, I've just argued that is not what's happening. It's the ocean lithosphere that's coming off. And I wonder around the world, how many of these are not crustal delaminations, but ocean lithosphere delaminations? A lot of them are where you've had subduction, um, under the region, perhaps flat slab subduction. And I see now coming into the literature, maybe especially for Turkey, concepts of, well, was this ocean lithosphere or was this continental lithosphere that came off? So we'll see where that debate goes, but at least in Oregon, I would argue it's ocean lithosphere that came off. Okay, the second lithospheric instability, a fairly simple one, and I'll go through this quickly. In this little cartoon, I show the buoyancy of the plume and other mechanisms I haven't mentioned, lifting this up and the heat and the magmatism weakening the plate. So here is a weak uplifted plate. And the idea is now gravitationally, it can basically slide off the top or gravitationally collapse with extension. And if you have extension with magma around, you're going to get diking. And I think when this extension happened, you would suddenly get a burst of magmatic activity. And that is, the extension happened during Grand Ronde time, especially, and that is the really big part of the Columbia River basalts. So here's a map of Eastern Oregon. You see all the dikes. These are the Chief Joseph dikes, the big producers. And you see the amount of extension that Leif Karlstrom and Matthew Morris get in Eastern Oregon, just counting up the extension in the dikes. Okay, so it really looks like this magmatic pulse of the Grand Ronde is associated with these dikes. These dikes are associated with extension. And I have to say, just one or two of these dikes would pretty much wipe out sigma 3 being horizontal and east-west oriented just by the stress that they would produce if they were in place actively. You need extension applied from the outside to keep this from happening. Okay, and here's just a little cartoon, I think motivated by some discussions with Ray Weldon. While this extension is occurring, it appears as though you have rapid shortening here in Central Oregon. And you look at the extension amounts, and it looks like there's a pole up here someplace allowing this wedge of crust maybe to rotate out and drive shortening in Central Oregon. Who knows, more work has to be done, but that's quite analogous to what we see today. Yellowstone now has propagated to Wyoming. That's where the concentration of extension is. And then you see the flow and you see the contraction up here in the Yakima Fold and Thrust Belt, about a pole not far different from this pole. The whole scale has just enlarged. Okay, the third lithospheric instability. This is after the CRBs, but related to them, and that's the foundering of the Wallowa batholith root. So you see faintly here the 706 line, accreted blue mountains out here. And I just outlined in this area the various granitic bodies in this otherwise accreted oceanic terrain. Okay, and the Wallowa Mountains in particular, and you see the bullseye around it and the moat and the central Wallowa batholith. All that being post-CRB, which you can see here. Here is the uplift. This is the uplift of CRB surfaces, which we take to be flat at the time of deposition, and we see them now at various elevations, elevated, low, and quite elevated in the Wallowas, up to 2 kilometers above the surrounding countryside. You can go to the top of the Wallowas and find a CRB flow. That flow is the same flow, the Imnaha, that you see at the base of Hell's Canyon over here. So obviously pretty spectacular uplift in the last 15 or so million years without associated horizontal tectonics driving it. So I sort of call this Russian tectonics back from their arguments back in the old plate tectonics days. And it's going to be attributed, I'll show you in a second, to the foundering of the route to the Wallowa batholith. Very similar to what Sue Kay or Jason Sleeby would say for other granitic uplifts in South America or the Sierra Nevada. You see in this cross section, purple is Imnaha, there's the Wallowa Mountains, and then you see Grand Ronde on top of it, and then here's the outer ring with the younger flows on top of everything. So pretty spectacular tectonics without much horizontal deformation. I'm not a geochemist, but here is a strontium to yttrium ratio. Remember, you have the strontium liking the plagioclase, yttrium liking the garnet. So this is kind of used as a gauge of how deep did the segregation occur of the granite from the basalt at depth. And this is a plot for Western U.S., various Western U.S. plutons, the Sierra Nevada and the Wallowa area in particular. And down here, we see that there is pretty shallow segregation of the granite. The plagioclase has dominated that geochemistry, but much of the Wallowa granites show the segregation at great depth, meaning garnet stability depths, so maybe down 40 or so kilometers. And the rare earth depletion pattern shows the same thing. So the point is, the Wallowa batholith was made by segregation that produced a garnet-rich, that is dense root, or whatever you want to call it. Okay. Again, back to anisotropy, but the idea is if the Wallowas lost their root to account for their uplift, and I gotta admit, it is the batholith, and only the batholith that really came up. It seems unavoidable to me, but if it did, you need a lot of crustal flow into this area to fill that evacuated area. And here's just some of the stuff that Jorge has produced to show the anisotropy for this particular station, just to show some results. I already mentioned that this anisotropy suggests a pull down of the crust here. So now I'm showing two possible sinks for crustal flow, and it's hard to separate one from the other. Maybe I'm fooling myself, but to me, when I look at it, if I get my pointer back here, here's a thick crust, and this anisotropy seems to flow into that area. You cross this blue line, and everything seems to turn around and point to the Wallowas. So perhaps we're seeing the flow excited by each of these crustal sinks for flow. Nonetheless, you would have to have crustal flow in to fill the evacuated area made by the loss of the batholith root. And one interesting thing, here are the Wallowas. Here is the Wallowa fault. It is technically a normal fault. Here it is in cross section. And every normal fault I know of, except for this one, the hanging wall dips down for good reason. And most of the lakes and the drainage all accumulates at the foot of the fault. Think of the Tetons and Ginny Lake and Jackson Lake. But here the hanging wall tilts up. Okay. My attempt to explain this is that around the Wallowas, the lower crust has flowed into this evacuation, pulling the moat down, as you see in this little cartoon with the flow of the crust. So here we see this up-tilted hanging wall, and the CRBs are right there, scratched below the surface. And so very unusual normal fault. Okay, so a quick summary for making the bullseye is the Farallon flat-slab delaminated. And when that happens, we suddenly have lost support to this root that was created. And that root now has the potential to founder. And it does around 10 million years ago, apparently. And as it founders, the Wallowa batholith goes up. And as it goes up, and as this hole is created, the lower crust flows in and pulls the moat down. So I think I forgot to mention the whole Eastern Oregon Plateau starts the story, and then you modify that in the area around the Wallowas. Let me see what's next. So here I'm sort of going into a sort of local summary. Local summary. And no pre-eruptive uplift. Maybe that's not surprising if the plume is below the slab. You have positive and negative buoyancy side by side, and they tend to cancel each other in terms of vertical force balance. The Sierra eruptions got off track and very quickly, which I'm attributing to south and north delamination. The volume increased as that happened, I'm attributing that to the gravitational collapse of the uplifted Eastern Oregon plateau. The backwards hotspot, we already considered that as entrainment and corner flow. And Yellowstone already made its flood basalt. It was Silesia. So we're attributing this to plume accumulated underneath the Farallon slab. That's a lot of patches. I asked rhetorically, are you happy with so many patches? Or do you think it's time to think of other models, other explanations for the Yellowstone system? Okay, so a quick local summary here. I just go through the buoyant plume ascends beneath Eastern Oregon. It lifts the ocean slab and creates these distinctive magmas for evidence. The plume arrival, when it finally gets past the slab, causes the CRB eruptions. I make the passing comment that this is compositional segregation. We're taking a lot of basalt out of the mantle and putting it into the crust. With continued refinement, we'll get granites and rustites. And so this is a basic process for making continent. Okay, but the plume triggers slab delamination. The slab is detached by the plume melt and descends based on the density of the slab. Delamination intensifies the magmatism and makes it propagate north. The magmatism gives rise to the uplift, which leads to the gravitational stability, which is the extension of Eastern Oregon, which gives rise to an amplification for the Grand Ronde basalts. The basalt addition to the crust, I guess I already mentioned this, is the initial step to creating continent. Later remelting will remake the granite into will remake granite and rustite. The rustite will return to the mantle. And this happened to the old batholith of the Wallowas. That granite was segregated, produced its granite and its rustite root, and it was left unsupported once the slab delaminated and it foundered. And so we finished the continental construction process at the Wallowa batholith. And that foundering of that Wallowa root draws in crust and drives crustal flow, which seems to be pretty mobile. Okay, to kind of step back one step, to me, there are two main processes that we're interested in the Earth. The mechanical side is just Earth's convection. That's driven by thermal boundary layers. The slab sinking and plumes rising. Plumes being about a quarter of the net, at least heat flow of the Earth, probably. So both important. And then the compositional segregation of the Earth, which basically means taking continents out of the mantle, and making the core. But speaking on the continental side, that's the two-way exchange, bringing basalt in, refining it, dropping out the rustite. And we see all of this action in Northeast Oregon and associated with the Columbia River flood basalts. And I sort of add that lots of unexpected things happened. So I think that might be about it. Oh, I just wanted to show one other side comment. Here is the Wallowas. And you look at the rivers, and it's amazing that they all radiate from here. Even rivers that seem to run all the way down the ridge of this mountain system. How do you do that? And, talking to geomorphologists a little bit, Kellen Whipple in particular, the most, the idea is the CRBs repaved the surface. So pre-existing drainages no longer existed. And then this area uplifted as a dome with rivers running in all directions from the top of the dome. And then following that, we produce the edge of the Wallowas with the Wallowa fault and truncate the dome and suck crust in and create the moat that you see bits of here and here. So to me, this drainage pattern suggests a domal uplift basically above this sill that we see at 9 kilometers. You see it here on a map for location. That allowed the high density root to founder, the granite to uplift, and the sill to be placed in between where there's relative tension. I think that might be it. Yes, that's the end. So I'd be glad to take any questions that people have.
All right. Well, thank you, Jean. That was amazing. Mindy says she's really looking forward to seeing the recording of your talk and that your graphics are amazing. And I agree, those are fabulous graphics. It pulls together a lot of things that trouble people about the Columbia River basalts. I think anytime you have a continent that overrides a hot spot, things are going to get complicated. So I'm not terribly uncomfortable with the fact that you have to put a lot of patches on the model. Does anyone have any questions?
I fear I may have overwhelmed the audience with too much stuff. Uh,
I can start to kick it off.
well, break the ice, yes.
I mean, I think this is a really useful way of asking the question, should we have to be unhappy about this? And you also make a very clear case for it's such an unusual, I mean, you get this really old inherited continent going over. So probably, I mean, I'm not uncomfortable expecting a lot of surprises. And the other thing is that it's really young and well preserved and well studied. And we don't have many examples. Maybe we would find this for any such young and well preserved and continental hotspot, but we don't have much to compare to. So how do we make progress on, deciding if we can be happy or not happy?
Yeah, no, I agree with all that. And I think it is unusually well studied, especially people like Vic Camp. Um, and if nothing else, for other flood basalts, now we have various processes that maybe you hadn't thought about that you can see, well, does this apply to Siberia, which seems to show no pre-eruptive uplift as far as I know, or other systems. So maybe it will help think about other systems. But and I also agree that this is a complicated area. You're involving a continent with accreted terrains and old history. And so in the end, I've grown comfortable with the idea that all the problems, quote unquote, are really little insights into how maybe unstable and interactive the continent is with mantle processes.
Mm.
So Ralph Dawes has a question. Is there seismic evidence for a sill under the Wallowas? If there is a sill, why does the crust need to flow in there?
Yeah, it looks like, I mean, the seismic evidence is imaging, and this is from ambient noise surface wave imaging, Rayleigh wave imaging, basically, from Haiyangao. So I think that sill, that high velocity body that we're calling a sill, is pretty well imaged. I think the root that founders is beneath that. This is the body that I envision separates the granites from the dense material beneath it, and then the lower crust flows in beneath the sill where the dense body used to be. That's my envisionment of it. I hesitate in a sense, as you know, our job is to make stories. And there's the story. And I have to confess, I have been certain of myself and wrong before. So this, uh, this is how I account for all that.
That's your story and you're sticking with it, yes.
Well, I stick with it until something convinces me otherwise.
Yeah.
Yeah.
One thing you said that is that there's some of the slabs still under eastern Washington, sounded like near the Idaho border.
Yeah.
Is that in any danger of delaminating, or is it now stuck there?
Well, good question. I don't know. Come back in a few million years and we'll see. It seems like it came off underneath northern Washington, associated with the Okanagan area. That's where all that volcanism was, and it stopped at the southern end of that, right where it should. For some reason, I don't understand that area well. If I go down to the southern end, the delamination ended right where the crust in the lithosphere gets relatively thin. And I could argue that beneath Oregon, the slab was deeper and the crust was eclogite. And by the time you get under Washington, perhaps it's too shallow. It looks like it would be too shallow for the basalt to have eclogized. Maybe the slab just does not have the negative buoyancy it needs to get off. Or maybe the Yellowstone plume that was being drawn in just gave what it could give and didn't have the oomph to keep going. I don't know. But it also delaminated beneath Montana and Idaho, giving rise to the Idaho curtain. And why it stopped where it did, I don't know. No.
Okay. So Keith Ronholm has a question.
Good.
Oh, hi. Great talk. My question regards the viscosity of the mantle with the Farallon plate, the flat plate delaminating and sinking. I did some quick numbers back of the envelope kind of thing. It would have to sink like 250 kilometers in 25, 30 million years, which is like a centimeter a year. Is the viscosity of the mantle sufficiently
Yeah.
light to let that happen?
Well, that has bothered me. I could turn it around by saying, in a paper just submitted to the Vic Camp volume, I could send you a copy if you email me. I show maybe a more realistic look at how I think the slab is coming off. But if this is North America and this is a slab, I don't think it does this. I think it must slowly pivot in some sense and decouple as you go across. But it is sinking relatively quickly. And if I take the view that this high velocity body beneath Northeast Oregon has to be Farallon slab, if I assume that to be true, then I would say this is kind of an experiment in how viscous the mantle is versus how dense the slab is. Those are your two parameters. And I'd say this whole system also is placed in an area where you have corner flow. So I don't know what the mantle wind would really be doing to things. It's kind of orthogonal to that, but you have this general, to the west or to the northwest flow of mantle across this region, which could help drive, inflate the area above the slab and drive the slab down. But that's a good question. I don't know. It seems ripe for some modeling and see what you get under those assumptions. Yeah.
Okay.
I got to add, my own personal opinion is I do think a cenosphere is fairly low in viscosity, maybe compared to some of the global, people consider the global viscosity structure. I'd say maybe 10 to the 19th Pascal second, something like that. And I think as people get smaller and smaller scale in their modeling, they are coming towards those kinds of values. So that would help.
Well, I think maybe we need a Wallowa field trip. One of these, I actually have never been there. And I kind of feel like it's a big hole in my Pacific Northwest.
It's such a great area. I have to say, I mean, the CRBs all around. You drive right over to Hell's Canyon or Joseph Overlook and see all these flows. You could take a tram to the top of the Wallowas or hike up to them. It's a wilderness area. And the picture I showed of the Wallowas with the up-tilted hanging wall is from Terminal Gravity Brew Pub, a great place to hang out and contemplate the behavior of the Earth. I'd highly recommend it.
All right.
Yeah, Karen.
Yeah, I'd like to ask another question. So the question will be, and then I'll explain it. So the question will be, what, in your view, is the relationship between this episode of flat subduction, which you don't doubt it happened. I don't doubt either. I mean, in the South at least. And so, what's the relationship between that and so then the Sierra Nevada batholith, etc., gets disrupted, and the inception of the Cascades arc? sometime shortly after 50 million years. And the reason I'm asking is I was trying, because for me, these are very separate, right? But I know I'm not in the mainstream with that. So I was going, as you were talking and saying, this slab that under the border of the three states is left over from the flat subduction. And I was playing this alternative hypothesis of why did it not come in with Cascadia arc sometime after it started, and I mean, it would also be Farallon, but it would just be more local, so to speak. And and I think you explained it. It's because there was no diffuse magmatism, no flare up in that region. Maybe I didn't get it, but so you can reply to all of that. But my basic question is, how do you see the relationship between this perturbed arc from the flat subduction episode and the clean Cascadia arc later?
Yeah. Well, I'd say several things. And maybe before I say anything, we assemble little pieces together to make a regional tectonic model. And so in my mind, all these little pieces aggregate together for my explanation. And perhaps you can pull some of it out. I don't know, but I have this integrated view. I would say you are right. The lack of magmatism in Eastern Oregon, to me, reflects that there's still flat slab there until the CRB event. It happened everywhere else where there was flat slab, in my view of things, but not there. And once Seleucia accretes, there's a big geodynamic change. You start subduction at the subduction zone. New subduction like that tends to produce a very tensile environment in the overriding plate. People like Gurnis and others have talked about it. This new slab, it's unanchored to the lower mantle. It's heavy. So almost always when you see new subduction, it wants to roll back unanchored and produce tension. And so all the tension you see in the Northwest right after Seleucia accretion suggests you have a slab steeply dipping that's now new. And Jeff Tepper in particular has looked a lot at models for this young subduction and seen some of the early magmatism in the early Cascade arc as old as 45 million years ago. Then the whole arc well established at 35. It seems hard to get the slab over to Eastern Oregon in that context to me. So the combination of that, the tension, the fact that this little fragment seems to bound all these mantle anomalies, I'd say delaminated slabs, it all just fits together in kind of a coherent picture to me. So that's my view.
Yeah. And I mean, so does that mean, would it be correct to say you think that the system gets clogged up in this Laramide episode by something that happens relatively far in the south with this Schatzky accretion? So then it stays quite messed up, maybe with some foundering. And then the accretion of Seleucia 30 million years later or so is what unclogs it, even though that's quite far in the north.
It's sort of, the accretion of Seleucia starts the ignimbrite flare-up. I think when Seleucia accretes and you start new subduction across the width of Seleucia, to the south, you still had flat slab subduction. I guess there's a paper a few years ago, Lunsney and Miller, I think, Elizabeth Miller, we talk about that, but you still had no magmatism in Nevada, for instance. And then from this tear south, you seem to see the propagating ignimbrite flare-up as the slab reestablishes itself. It rolls back or delaminates, or whatever you want to call it, across Nevada. Okay, and it rolls back and establishes the ancestral cascades behind the Sierra Nevada, far down into the Owens Valley, far south into the Owens Valley. And then as the triple junction migrates north, the cascades migrate north with it, and a lot of the ancestral cascades stop. I think, to me, the chassis conjugate did go underneath the southern tip of Sierra Nevada, northern Mojave. You've probably seen that, and end up beneath Wyoming, which isn't very far from what we're talking about. I mean, beneath Wyoming, the Montana alkali belt is kind of where the Idaho curtain rolls up to, right adjacent to that. So it's all one big picture. But anyway, to get back, I think the accretion of Silesia does initiate one, the ignimbrite flare-up in the northwest, and two, this tear that now can roll back across Nevada and propagate the ignimbrite flare-up south across Nevada. There's another half of that in Arizona. I'll skip for now.
Okay,
That
thanks.
answers your questions, but I fear that you're seeing my integrated view of the world, and I think somebody like Basil Tikoff would say, well, what happens if you start pulling some pieces out? Is this a house of cards or is this an integrated explanation?
Well, I think the flat underplating makes total sense. I'm just worried about what happens behind that. Is the Farallon plate really still coming in? And that's for me hard to envisage that there's still substantial incoming when the system is clogged up and there is no arc. But that's
Yeah.
that's
It appears, and I agree with Elizabeth Miller on this, that once Silesia accretes and you produce that tear, you continued
yes.
slab subduction under Nevada, so it's still subducting, but without an arc because it was flat slab, gets based in North America. But almost immediately at the time of that tear, you start seeing magmatism propagate south and reestablish a normal subduction zone and ancestral cascades. That's I think how I see it, and I think how Elizabeth would say also.
All right. Well, we had one more question in the chat from Karen. Is the CRB flow west to the sea simply gravitational response to an existing drainage system?
Is the CRB flow? Well, if the flow north is going downhill into the Columbia embayment, if I'm understanding, and then it does hit the embayment, and it does flow all the way out to the sea, and it's all downhill flow. There's an intervening story in there, and that's the Pasco Basin, which I completely took out. But this basin subsides rapidly during the course of the CRB flows, accumulating up to 4 kilometers of basalt. And so we do have a little paper about that in geology, with Jonathan Perry Houts being the lead author. And not to say the whole Columbia embayment is a subject that Ray Wells and I are currently starting to try to work on. Well, we are starting to work on it. We'll see where we get.
Okay. A future talk.
Yes. Yes. But the simple answer is yes, it's all downhill flow all the way to the Pacific, right over what is now the Cascades built over the top of that. If you've ever been to Silver Falls, that's a fantastic place to go.
Yep. Malala River too.
Yes. And yeah, Haystack Rock, I think, out in the Pacific is CRB flows. And it's pretty amazing to me to think that flows from Idaho made it to the Pacific Ocean.
Yeah.
In this small flood basalt. Relatively.
To make it through the Cascades. They made it through the Cascades, but they also have to make it through the Coast Range in Oregon, because you see it all the way as far south as Seal Rock, and you see it about at that same latitude in the Willamette Valley, and you know that it didn't go down to that latitude in the Willamette Valley, and go out to Astoria, and then go down the coast to that same latitude.
Right.
But I've been trying to find, and I can find lots of examples of basalt in the Coast Range, but all of it has been testing out as Silesia.
Yeah. I guess, Ray Wells has that paper from 2014. Either Silesia hotspot created, new subduction created as a second phase, and his third phase is an overriding the hotspot again with, Tillamook Yahats kind of stuff. The Coast Ranges are coming up. And the idea is this subduction is hydrating the mantle beneath the Coast Ranges, increasing the buoyancy. But a lot of the rivers, the Siuslaw River goes right across the Coast Ranges, and as the Coast Ranges come up, it's kept its course. The McKenzie River used to go across the Coast Ranges, but it's been captured by the Willamette.
Yeah.
Yeah, so it's interesting.
And the Willamette has been pushed over. I live in the Willamette Valley, so I'm looking at all the basalt. The Willamette has been pushed over so many times by the basalt coming in.
Yeah.
That's what makes the Eola Hills and the Salem Hills is it finds its way through, but it's been pushed over. Same thing with the Chehalem Mountains.
Ah, Ray Wells, and you could have a great conversation, but the whole Willamette Valley Coast Range story is a really interesting one. I'd like to hear
Yeah.
later more.
Yeah.
Sounds like you're the one that should give the talk.
Could be. So Sheila, has it been pushed further east, the Willamette River?
Say
Or
that
you said the Willamette has been pushed, but
Yeah.
is it eastward that it's getting pushed?
is it what?
Is it eastward that it's getting pushed?
Well, the basalt comes obviously, up the Willamette River, so it's pushing north. But right at
Oh,
when you look at the mountains that it makes on the northern section of which is the Eola Mountains, the Willamette River is on the east side, and then when you get to Independence, the Willamette River is on the west side and it goes right through. So it cuts right through. And that's where we put Highway 22 that goes to say, we made use of it. Does that make sense? It pushed over the river, but it pushed the river, aside to in the northern section of the Willamette Valley. It pushed the river to the west.
oh,
No, excuse me, to the east.
Oh.
And then in the southern section, it pushed it to the west.
well, that sounds like a real interesting story to hear.
And then I'm also really intrigued with the Chehalem Mountains because if you look at the Tualatin River starts way over near Yamhill, where I lived for many years, and then it goes up north to Forest Grove, and then goes around, and then turns into the Tualatin, what we call the Tualatin Valley. But that's all. The Tualatin River was pushed over by the Columbia. That's all Columbia River basalt and the Chehalem Mountains.
Mhm.
And I think it's interesting because it follows the same fault line as all the other strikes that faults through Oregon. It follows a trend of northwest to southeast.
I'd really like to hear your talk.
Yeah, I'm gonna put together. I'm gonna call it "Move Over River." Here I come. Because all these rivers have been pushed around by displaced by basalt coming in.
Yeah. The Cascades have come up a lot with time. I think it's the only volcanic arc in the world that has a major river crossing it.
Yeah.
Yeah.
Yeah. All right. Well, are there any more questions?
Well, I do have a local question about Southwest Oregon as I've been trying to learn about it. We have the Western Cascades, which become active about 35 million years, I think, and continue until 15 or so. And then they cut off, and there seems to be compression and tilting of everything until then about 7 or so, the modern cascades start up again farther east. And I've never really seen a good explanation for what was happening in that kind of, 10-ish time to cause contraction across the margin in this part of the arc.
Ray Wells has several excellent papers on that.
Yeah, rotation of the coast. The rotation.
Okay.
Sierra Nevada,
Okay.
some gets entrained and pushes up. The Sierra Nevada Klamath Block moves, northwesterly, rotating the coast ranges around, pushing the Western Cascades to the west. and extension behind it in the basin range as it creeps into the Cascades, right into
Yeah.
lake area. Really fantastic story, but he has a series of papers on that. And I reviewed some of those in a summary with Anita Grunder recently in Bolton of Volcanology.
Yeah.
Is the fastest way to find those references.
Oh, great. I'll look at that. Thanks.
Oh,
Yeah. Okay.
all right. We have another vote for hearing someone explain the drainage patterns in the in the Willamette Valley. I assume that will be a GSOC talk.
I'd love to have you do a GSOC talk, Gene.
A what talk?
Geological Society of the Oregon Country.
Oh, okay.
And we meet in Portland, and
I know about this group. Yes. If it comes to the dinner, I'm game.
we have dinner. We offer dinner. Yeah, Rob McCaffrey is the one who did all the GPS stuff to see the rotation of the Coast Range. I'm glad you mentioned Rob. He was also a GSOC member.
Yeah.
And John Sharman is asking who wrote the paper about the rotation of the Pacific Northwest. I think it's Ray Wells.
Ray Wells did, but Rob collected all the data, and he gave a talk on GSOC about it a long time ago. But then Ray really put it together.
Right. There's a paper, Wells and McCaffrey. No, that's good. Like I say, all that is listed in that one review paper. Yeah.
All right.
Thank you very much. That was very interesting.
Well,
Yeah,
thanks.
there are
Thanks
lots
so
of
much.
thank yous
Fabulous.
there are lots of thank yous in the chat if you want to look at them before I shut down the meeting, Gene.
Okay, see what I can find here in the chat. There we go.
Yeah.
Thank you, 23. Okay.
Well, and you
Sure.
could send him the text of the chat too.
Yeah, I could. Anyway, I'm going to shut down the recording unless somebody else has a question.
Okay.
Okay.